This is the periodic table of elements where the relative size of each atom is represented by the size of each disk. So in a way, this represents the radius of the orbit of the outermost electron in each atom. The number in a periodic table is usually the atomic number, but here the numbers represent the radius in picometers. I wanted to point out something about the sizes here. You'll notice from this graph that carbon is a relatively small atom with a radius of 67 picometers. You'll notice that germanium is larger than silicon, and silicon is a larger atom than carbon. So using the size, you can get some idea of the work function in a solid too. The fact that the carbon atom is smaller than silicon, this is interesting. Here's the electronic structure. Carbon, silicon, and germanium are all group 4 elements on the periodic table. They're group 4 elements because if you look at the outermost shell, there are 4 electrons, and there are 4 openings, or slots, if you will, for electrons in the outermost shell. The only real difference between these atoms is the size, but their chemistries are very similar because it's the outermost electrons which interact with other atoms the most. Diamond is a lot harder than silicon, and it kind of makes sense, right? The atoms are closer together, so the bonds are a little bit stronger when they're combined into a solid. It doesn't mean that you can't break diamond. Of course you can break diamond. It can cleave. You can cleave it along a crystal plane, but it's certainly a lot harder to do that than it is to break a silicon wafer. So I have some silicon wafers with me. Silicon is commonly used in the microelectronics industry. Silicon wafers are single crystals, and they come in a variety of sizes. I have one here that's a 4-inch wafer, and then I have a bit larger one here, a 6-inch wafer. And if you look at these wafers up close, they look almost like a mirror because they've been polished. And sometimes wafers are polished on both sides, and sometimes they're polished only on one side. Anyhow, the processing of the silicon wafer into a bunch of microchips is always done on the polished side of the wafer. Silicon is obviously not transparent. The wafer that I'm holding right now is just polished on one side, so if I turn it over, you can see that the reflection is quite a bit duller because the back side hasn't been polished. Now this silicon wafer, it's quite large, and believe it or not, it's a single crystal. There are practically no dislocations or any imperfections in the crystal at all. It means that nearly every single atom in the entire wafer is properly positioned in a lattice. If I were to crack it or to cleave this wafer, it would crack all the way across and give me a perfectly flat, atomically smooth crack. So let's go to the clean room and crack or cleave a piece of silicon. So I'm going to nick the end of this wafer a little bit and then apply just a bit of pressure on one side of this piece of silicon. And now you can see that the crack is really flat. That's called cleaving a crystal. And one of the reasons why you know the electronics industry has progressed so rapidly in the last few decades is because of the technology involved to grow these silicon wafers. Wafers are just slices of crystal sections called boules, and they're practically grown in a big vat from a very small seed silicon crystal. They pull out the material from the melt as it hardens, and then they slice up the resulting crystal into wafers. So what I'm holding in my hand right now is just a cross-section of a giant silicon single crystal that's been pulled out of a melt. I don't know if you've ever grown salt crystals or sugar crystals when you were a kid by using a piece of string dangling in some water where you have either salt or sugar dissolved, and then you hoped that you would get a giant salt or sugar crystal attached to the string clinging on once everything's dried up. It's the same sort of a deal with silicon, and you hope that you get a giant crystal of silicon. It's bad if you get lots of small crystals, for instance. If you've ever grown salt or sugar crystals, you know that crystals can grow in several different orientations, and you might end up with some growing together in clumps. So with silicon, it's been grown in a very controlled way, so as to get just a single crystal. I've got a piece of diamond too, and it is possible to grow diamond in the lab, but the quality isn't as high as with silicon, and the size of the crystal isn't as large either that's capable with current technology. Now, I've just pointed out that silicon has the same sort of structure as carbon and also germanium. Hydrogen is also an element with an incomplete outer shell. If I draw the same sort of diagram for hydrogen that I've drawn for silicon, it only has one electron in orbit, and there's room for one more. The inner s orbital is only half full. If it were helium, on the other hand, then there would be 2 electrons in orbit, and the outer shell would be completely full. One of these electrons would be a spin-up electron, and one would be a spin-down electron. So because it has this hole or opening, this is why hydrogen atoms tend to team up in groups of 2. H2 in a gaseous form is a really stable compound. Now, if we look at carbon and I draw only the outermost shell, and we're going to neglect all the inner orbitals for the moment, then we have 4 openings and 4 electrons. This is one way to draw the outer shell. You can imagine that a hydrogen atom might be attracted to this opening, and this opening might be attracted to this electron. So this kind of forms the basis of organic chemistry, you see, because carbon has 4 bonds and hydrogen fills them in really well. So let me now draw it in a slightly different way. This is how they typically draw it in organic chemistry classes. Since we know that carbon has 4 bonds, and we know that hydrogen can fill these bonds, one very simple organic molecule is CH4, or methane. Methane is a gas, and each carbon atom has 4 bonds, and each of those bonds is with hydrogen. If we were to have 2 carbon atoms, then the compound would be called ethane. Methane is a gas. Ethane is also a gas, but it's a heavier molecule, it's larger, and it has a lower boiling point. Let's go ahead and draw the next one with 3 carbon atoms. This one is called propane. And as the molecules get larger, they also get heavier. So eventually they're going to start becoming liquid at room temperature. And in fact, with 4 carbon atoms, which I'm not going to draw, we have what's called butane, which is used in cigarette lighters. It's a very nice molecule because it's almost liquid at room temperature and atmospheric pressure, but not quite. But the small amount of pressure from a cigarette lighter container is enough to keep butane in a gaseous form when it's released, but to hold it in liquid form when it's still in the container. Without the pressure of the container, cooling the butane down to below 0 degrees Celsius would be enough to keep it in liquid form. So if you were to open a cigarette lighter on a cold winter day, the butane wouldn't boil away. As the number of carbon atoms increases, the molecule, or the hydrocarbon, will first become a liquid, as in gasoline. You might have heard of octane, which is the molecule that would have 8 carbon atoms and is a constituent of gasoline. As you get longer and longer carbon chains, you start to get into heavy fuel oil type things and eventually paraffin wax. I think it's very interesting because these long carbon molecules are very stable and they form the basis of all life in all organic chemistry. But people have thought about this before, because carbon has an electronic structure very similar to silicon. And could it be possible on some other planet that silicon life forms could have evolved? Is it possible for silicon to replace all of the carbon that we know in organic chemistry and give the rich complexity of molecules that are needed, for example, to form long chains of amino acids, DNA, and everything else like proteins and enzymes? Nobody really knows, but it's probably difficult. So let's make a similar drawing of a simple organic compound, but with the carbon replaced with silicon. Of course, the same molecules exist because silicon has the same outer shell structure as carbon. This molecule is called silane, SiH4, and it's actually a really dangerous gas. The next one with 2 silicon atoms surrounded by hydrogen is called disilane. With 3 silicon atoms, which I won't draw, it's called trisilane. I know these are very creative names. Silane is a lot more volatile than methane, and the reason is because silicon is a bigger atom. So these bonds to the hydrogen atoms at the periphery are not quite as strong as they are with methane. Silane is used quite a lot in semiconductor manufacturing. They use it as a precursor to make silicon dioxide or glass coatings in the electronics industry. So silane is kept in gas cylinders. At room temperature, silane will pretty much self-ignite, whereas methane is fairly stable. People use methane for cooking. It's called natural gas. You wouldn't want to use silane for cooking. Silane fires tend to burn down buildings and cause millions of dollars in damage when they happen. So basically, silicon forms larger molecules than carbon does, but these molecules tend to fall apart. So when people have thought about, well, would it be possible to have silicon-based organic chemistry or silicon-based extraterrestrial life forms? The answer is that these molecules are really unstable at temperatures here on Earth, and the bonds silicon forms naturally with other elements are also more unstable compared to those of carbon. So there wouldn't be the same variety of molecules, even at really low temperatures, where things tend to be more stable. But whether there would hypothetically still be enough variety such that silane-based life forms could exist in principle is still an interesting idea to think about. So lucky for us that carbon molecules are stable, because it's really handy for life on Earth. Now let's look at the periodic table one more time. So silicon is in group 4, carbon is in group 4, arsenic is in group 5, gallium is in group 3. So it turns out that if you combine gallium and arsenic, you'll get something with the same sort of structure overall as what you get with the group 4 elements, because arsenic has 1 extra electron in its outer shell, and gallium has 1 fewer electron in its outer shell. If you mix them together in a 1-to-1 ratio, you'll get something like a group 4 element in the resulting crystal. Let's look at the structure of silicon in solid form. Now, I've only drawn here the outermost orbit of the electrons in the silicon atom, and I've also kind of flattened everything out. Obviously, real silicon atoms combine in a 3-dimensional structure, which is hard to represent in a 2-dimensional diagram. And if you look at these silicon atoms that are in the interior and you put them together, you can see that we have a completely full shell or orbit around every atom of silicon. Now, this is the lowest energy state of silicon. It forms a kind of diamond-like crystal structure, except that the atomic spacing is greater than it would be in diamond because each atom is larger. The bonding is thus not quite as strong, and the crystal isn't quite as hard as diamond is. And of course, the spacing is going to be a little bit different in the interior. There aren't any more silicon atoms at the surface, so these open states will be dangling bonds. And this is why surfaces are always different than the interiors of crystals. And it's also why the work function of a crystal is related to the electronic structure at a surface rather than something deep inside the crystal. These dangling bonds at the surface of a crystal of silicon mean that silicon will react with its environment. These dangling bonds can react with oxygen, for example, forming a very thin layer of silicon dioxide or glass at the surface of a piece of silicon. Or they can react with hydrogen atoms or a lot of different atoms, really, depending on what's available to donate electrons to the silicon at the surface. The crystal structure here of silicon or of diamond is very similar to that of germanium. It's also very similar to that of gallium arsenide, where you would have every other element, either gallium or arsenic. In gallium arsenide, each gallium atom has 3 electrons in the outer shell. Each arsenic atom has 5 electrons in the outer shell. So combining them gives a full outer electron shell.